people come. So, we will take the next problem. We started yesterday about how the force is transmitted through a slender beam, and we defined what is a beam, what is a slender beam. Then at any cross section you have in a beam which is lying in a plane xz, that is there are no loads perpendicular to xz plane. So, in that case, at any cross section you have three forces, that is one bending moment, one shear force, another one is axial force that exists along the length of the member. Now, today we are considering a simply supported beam subjected to UDL, uniformly distributed load. Now, I have specifically put this minus P naught, it is acting downwards. So, as per our sign convention, it is negative. It is not in z positive direction, it is okay, it is not in the direction of coordinate x, y, z. So, it is just for your reference, but you do not have to worry about it. What I am saying, you have to worry only about the cross section, positive shear force, positive bending moment at any cross section x. At any cross section x, I must draw my free body diagram, and that free body diagram at any cross section, what are the positive, if I cut it, so then the positive shear force is like this, positive axial force is like this, and positive moment is like this. This is my sign convention which I took it. So, this is positive. So, I will retain this, that at any cross section you have. So, we have to draw, or we have to study the variation of bending moment, shear force, and axial force along the length of the member. So, I have drawn this. See, it is also sometimes because loads are always put on the member, so they will always be downwards. So, what I am saying, do not think of load that is acting upwards, because it is okay. So, it is all right. It is also shown like this. There is also a instead of you show it like this, UDL, uniformly distributed load, or you show it by this. So, you have the beam is shown by its centroidal axis, a single line, and then this is the loading acting on it. This is the free body diagram, second one is the free body diagram. There are two reactions here, one reaction over here. This one, a roller also is shown like this, the way I have shown here. Either you show only a simple roller, round, or first you show a hinge and put the hinge on a roller. Okay. So, that means this x direction movement is movement, not moment. X direction movement is allowed. Okay. So, this is all right. Now this is the equivalent static load acting on this is P naught L, which is acting, the line of action is here in the centroid. So, this is the equivalent static force diagram. Now, equivalent static force diagram will give you the reactions right if you draw on the entire structure. Okay. Just they can be drawn only for the reactions, but not for the bending moment and shear force at any cross section, because there the effect of this wearing load will be needed. Okay. So, this is all right, this is the equivalent, P naught L is acting here. So, now for this you find out, you sum all the horizontal forces, that is the first equation. Now, you get here Ax equal to 0, because there is no other force in x direction. So, Ax becomes 0. Sum all the vertical forces sigma v, I write it sigma v also, it is written simply like this, v means vertical, h means horizontal, all forces vertical direction. So, you have Az, Bz minus P naught L. This is the second equation that you are getting. Is it okay? Second equation of equilibrium. And third equation of equilibrium, you take moment of all these forces that are acting on this body about a point. Now, I have chosen a point A for simple reason, because there are two reactions which are passing through it. Otherwise, you can take any other point, but then there will be more calculation, that is all. So, here this one will not appear in your moment. So, I take moment about A, this is my third equation. So, that is B z into L this way, and then P naught L into L by 2, lever arm is L by 2. So, these are the three equations, and you get from the third equation. By the way, what is the lecture is okay? Yesterday was 18th lecture. Check up, write it on your notes. 19th. So, all right. So, this is so from third equation we get from third we get Bz equal to P naught L square by 2. This is P naught L square by 2. I hope you can see it. P naught L square by 2, L anyway divided by L. So, divided by L, and yes, that goes, it has to be divided by L. So, multiply divided by L. So, you get here P naught L by 2. So, you have got, and therefore, from second equation, from second equation, therefore, from equation 2 we get, equation 2 is what? Az plus Bz. So, Az is equal to P naught L minus Bz, and therefore, P naught L minus P naught L by 2, and that is P naught L by 2. Therefore, the reactions are now computed, and we have got, this is the beam, of length L subjected to load P naught. The reactions are Ax equal to 0. So, this is the free body diagram, and you have got everything. Now, next is, please find out the values of. So, from the left hand, now I would like to draw at a distance x cross section, draw the free body diagram. So, this is your beam which is in subjected to, one end is subjected to P naught L by 2. Now, I will appreciate if you stop talking. Okay, some of you are talking in. And then here at this cross section, this is the cut section. So, this is a positive So, you have n, you have q, and you have m. All these are functions of x. Three forces, they are all functions of x. Okay. So, what do you get? So, you get take equilibrium, because this portion is in state of equilibrium. This cut section which is of length x, from here to here it x, this is of x length, and this is in a state of equilibrium under P naught L by 2 I applied over here. P naught UDL is moving over x, and then these are the three unknown forces that are acting over there. So, under the action of this is in a state of equilibrium. So, please apply your laws of equilibrium, and you get here first sum of, please write this whenever you write in your notebook or exam paper, please show this. Yes, the first equation you are taking this sum of all forces. So, you get that n equal to 0, because this gives you n equal to, there is no other force except n, there is only one force n. So, n is 0 first. There is no axial force. Vertical, sum of all vertical forces equal to 0. This is my second equation of equilibrium, and you get here P naught L by 2 vertical force in z direction. So, I am taking positive. Then here, because of UDL minus P naught into x, this force will be how much? P naught per unit length multiplied by x is the downward force. So, with the negative sign, plus q vertically upwards. I think that is all. So, we have got this second equation. Now, here there are two unknowns. So, this is equal to 0, but then this contains how many P naught? This is yes, no, I think we can get the value of q here. So, from here you get the value of q. This gives you q will be equal to P naught into x minus L by 2. Check up whether it is right. So, we get here when x equal to 0, q equal to minus P naught L by 2. When x equal to L by 2, it is 0. When x equal to L, it is P naught L by 2, changes sign. So, it starts with a minus sign, goes to 0, and then again becomes positive. Okay. So, the variation of this quantity, is it okay? Q, how does q vary? Q has a linear variation because it is only a function of x. This is the expression for q. Q is a function of x. It is varying because we are trying to find out variation of shear force along the length of the member. So, once you have, so you please draw this. You should always draw it and understand why it is happening and why it is minus and why it is a plus. I am going to ask you this question. So, somebody, okay. So, this is variation is when x equal to 0, it is minus. So, minus P naught L by 2, then 0, and then it becomes plus P naught L by 2. Join this by a straight line. So, this one is minus, this is plus. So, this is SFD, shear force diagram. It varies like this. Why should it be minus at the support, at the left support? Let the attendant, okay, it is going on. Yes, please. See, What is your positive? We have taken if this is your cross section and this is your x direction, in that case the positive shear force is this. This is Q positive. This is a sign convention. On the positive phase, Q is positive if it is in the positive z direction, positive coordinate direction. But here it says at the support it is negative. What is the meaning of this? Support it is negative means, so if it is positive here, but then on a negative phase, supposing I cut the member, you see, and I want to draw shear force on a negative plane. What is the negative plane is this? This is x direction, so this is my negative x plane. What is positive shear force on this? If it is this, because when you bring these two ends together, they will nullify, is it not? This end and this end will join together. You have cut it here, so this one is the positive, this one is the negative. So this is Q positive. Again, this is also positive, this is also positive. Now here it says that at this end it is, I mean this Q, see drawing of, I am trying to show you why it should be. So if this is the beam length, what will you call this end? This is a positive x. This face is what? If I cut it to the support, negative x. Negative x. Load is acting like this. Load is downwards. So a shear force which is coming negative, I think this is PL by 2 here. What is the direction of the reaction here? It is because this is a downward force, P naught into L, equivalent force is P naught wall downward. So here on this negative phase, a shear force which is upward. So this is a negative plane. Negative plane, what is this direction? Is it positive or negative? Just now we drew this. Yes, this one is positive. A downward force will be positive. Is it okay? But upward force is negative. So that is why this shear force is coming negative. So this value is negative here, because a force on this negative x plane, a force whose direction is upward is acting. Is it clear? Why it is negative shear force? How many people understood this? Raise your hands. Nobody, except one. That's very sad. Do you understand that this force is upward at the support? It is a cut, it is a free body diagram. What is this? What is this face? This is negative x direction. So it is a negative plane. What is the positive direction of shear force on a negative plane? Downwards. It should be downwards. Yes. Why it should be? Why you are putting a hand like this? Yes. downward from here, from the sign convention. See, if you cut it, if you cut a member, because if you do not understand this, you will never understand. If you do not understand it now, let me draw it once more. Now I am showing also the depth. I am drawing a free body diagram of left and right separately. So, this is the up to x, and now I am displacing the right hand side, I am slightly displacing over here just to make matters clear. Otherwise, I have no intention of, do not think that there is a rigid body motion or. So, this one is displaced, this is the cut, this is the same x, x is both. Okay. Now, at this, on this, what is a positive shear force? What is a positive shear force here? Downwards. When you bring them together, then they nullify each other. When you join the members, it becomes one, and Newton's third law says, they must be equal and opposite when they are separated, but when you join them together, they will nullify. So, when you bring them together, so this is positive, this shows a positive. What about this end? On this side, this is negative. So, this is similar to this face is similar to this face. So, this face positive is here. So, this shows complete positive shear force. On this element, the positive shear force on the positive x face is upwards, negative x face is downwards. On this longer member, on a negative x face, the shear force positive is downwards, and on the positive x face, positive shear force is like this. So, this is also showing positive. So, these are the directions of positive shear force. Everywhere you cut it. Now, here you are getting, as per calculations, here you are getting negative PL by 2. So, only thing, negative PL by 2 means at this end it must be opposite of this, and it is opposite. It is like this, it is upwards. Reaction is acting upwards. So, reaction is a free body diagram, what is there at that end. On the negative face at A, at point A, you have a force that is going upwards. So, this PL by 2 is negative, because positive must be downwards. Now, what about this end? Here, the reaction here is free body diagram, you have got it. Reaction here is again P naught L by 2. On this face, it is P naught L by 2. So, what is this? Positive. So, that is why you are getting positive. So, shear force diagram, it changes, it becomes 0, and then it then bending moment. Then bending moment. So, this is your, see, I am showing the depth only to make things little clear. Depth is small compared to the length. You have the center line here. Now, you have the free body diagram. So, free body diagram is Now, let us concentrate on bending moment. So, I want to find out at the cross section x bending moment. So, let us again draw the free body diagram of this portion. So, I will take this. Of course, there is a load, do not forget to put the load, then only it is in a state of equilibrium. So, there is a load, then reaction, once you have shown the actual direction, then there is no confusion. Do not try to put it positive, negative, do not show here negative, positive, then you will go completely wrong. You have already shown the direction, clear direction, yes, it is acting upwards, it is okay. Yes, as per your sign convention, this is negative, does not matter. Yes, this is keeping this load. Now, for this, the bending moment for my convention is this is my M. Of course, you also have shear force here, because otherwise this element will not remain in equilibrium. This element will not remain in equilibrium just with this. This is partial free body diagram. You have to show this and also show this. Of course, some are 0. So, this is in a state of equilibrium. So, this length is x. So, therefore, the load is, so bending moment. So, I consider the equilibrium of this. This element is in a state of equilibrium under the action of the forces that are shown. I do not want to have unnecessarily bring in this unknown force Q as well as unknown force N. This is N and this one is Q. So, best thing is I will take moment about this point, take moment about the cut section, take moment of all forces about the cut section. Is it okay? You will not lose M, by the way. M is acting. M is an external moment. The forces passing through that point have 0 moment, but moment will remain. You have applied moment there. So, there exists a moment there. Internally, there is a moment. Moment will not be 0. At that cross section, there exists a bending moment, M. So, I take moment about this point. So, take moment about and why do you take? Because I do not want to have Q and N in my calculation, honestly. Otherwise, I can take moment about this, again you will have to do eliminate and this. So, take moment about cut section at distance x from left hand support. So, if you do that, if you take moment about this point, so you get one is P naught L by 2 is acting over here. So, multiplied by distance is x, this multiplied by x. It is also a good practice to show the direction, so that you are taking moment about this moment is like this, clockwise, just for so that you do not make mistake. Then moment, because this is a UDL that is acting, so centroid of that will be at a center. What will be centroid? at P naught at x by 2. This is a UDL, so the center of gravity of this load is here. So that will be plus or minus, that will be minus. So minus P naught x is the load multiplied by x by 2. This distance is lever arm is x by 2, half of this. Is it clear? Lever arm from this point to the centroid is x by 2. So this is P naught x, x by 2. This subject is not history, it is pure mechanics, pure simple calculations. So you have to be careful about which point you are taking moment, where is the force acting, what is the lever arm, what is the force value. So these things are important. And don't take the book of solid mechanics and read like this. You know, when you have to sit on a table, open the book, keep some papers with you, read and draw the diagram, do some calculation, then only you can learn. Okay? So it cannot be learned by just reading like this, you know. Okay, so this is the moment about this point of this UDL. Then what else is there, please? This is negative. Anything else? Yes, this moment is there. About this point we are taking, moment means about which point, which axis you are taking? Y axis. Moment you are taking about y axis. Please be clear. Perpendicular to the plane of the paper. So you are taking moment about y axis. So this moment is there. Moment existing at that cross section. So plus m. Anything else that is acting? Is there anything else? Yes, moment of this n will be 0, moment of q will be 0, so because they are passing through the same point. So this is all right. So this is equal to 0. And therefore, m is equal to P naught x square by 2 minus P naught xl by 2. I think it can be simplified. So P naught by into x can be taken common, this much, x minus L. Yes, this is all right. So it is a quadratic variation in x, linear plus minus quadratic. So variation is quadratic. Bending moment diagram varies quadratically along the length. By the way, this is valid from this all that we are deriving, because there is no other, you know, concentrated force or anything, you know, that will. So it is valid for all the sections up to L. Okay, so all these calculations are valid from 0 to L. X greater than 0, x less than L. These calculations are valid for x greater than 0, little greater than 0, and x less than, little smaller than L, not exactly at the support. You cannot do that. So this is all right. Now what is this variation like? So this variation try to plot this. Try to plot this over the length. This is the length x. Sorry, the line is not drawn horizontal from these two ends. When x equal to 0, yes, it is 0. x0 equal to 0. When x equal to L, this is also 0. In between, whether it varies positive or negative, that we have to see. So x, it is negative, bending moment is negative. Yeah, you will see. So, when x equal to, let us say, L by 2, when x equal to L by 2, at x equal to L by 2, m equal to P naught L by 4 into minus L by 2. So, that becomes P naught L square by 8 with a negative sign. So, center it is something here, negative. Negative means this is positive, this is x, this direction is positive, this direction I am drawing above and below. So, if you plot the entire thing, you will get a quadratic 0 here, maximum in the center. See, it will be maximum in the center, and this will be a curve like this. Why should it be negative variation? That means whatever moment we have drawn, this at this cross section, that means moment direction is opposite of that. Why should it happen? Can somebody explain? This direction is not right. What is this kind of moment producing? Tell me. If I have a beam and this cross section moment is like this, what it will produce? See, this is the end and there is a moment acting like this. What it will try to? Will it not try to stretch the top fiber and compress the bottom fiber? Is it okay? So, top fiber will be in the tension and bottom in compression. Now, when you have a loading like this, what is the kind of deflected profile of the beam? Deflected profile of the beam is, it deflects like this. Under, when the load is there, the beam deflects like this. If it deflects like this, and if this is the depth of the beam, I am drawing only to support, what is happening to top? Compression. So, this one is compression, this is tension. So, it is just the reverse. While a positive moment, whatever you have assumed, produces tension at the top fiber, compression at the bottom, while this moment the loading is such that it is producing compression at the bottom, and therefore, at any cross section here, if you draw, because this will be the bending moment at this will be like this, and this direction is opposite of what you have assumed. What you have assumed is positive. Always work with positive. Is it okay? Why it is negative? So, always positive and negative is related to the behavior of the beam. So, when we have assumed, so this means what we have assumed positive, please see, I am taking a small element of the beam. I have cut at a distance x and x plus delta x, so that this length is dx. Is it okay? This is what is positive bending moment here on this section as per our convention. it okay? This positive, why? Because it is a positive phase, positive x phase, and we have assumed this is moment. This is negative phase. What is the positive bending moment here? It is something like if you cut, I think here, this diagram I had displaced the two members. Is it okay? So what is positive bending moment on this face here? Downwards. Is it okay? Like this. What is positive on this side as per Newton's third law? Opposite. If this is clockwise, this must be anti-clockwise. If there is axial force in this direction over here, there must be equal and opposite, so axial force must be like this at any cut section. So what is, and this is negative phase, this is the negative phase, this is a positive phase. So on a positive phase you have, this is my positive, on a negative phase this is the positive. So this one is negative phase. If you take a small element, that means if I cut a small element, so this is positive and this one is negative. I have already shown here positive. And on this one will be similar to this. So what is bending moment positive over here on a negative phase? So this is positive. This bends the beam like this. Sorry, I'm sorry. Yes, you are awake, huh? Yes, so this is positive. So this is, the action is this. While the given problem it is just the reverse. The beam deflects like this, and therefore instead of convex, this is which one is convex? This is convex, this is concave. So convex is on the top, concave is on the bottom surface. While in this case, in our case, if the loading is like this, you have just the reverse, and that is why the bending moment is negative. Now it is a different matter that somebody will call that as positive. We have taken this convention, so we will follow this convention. Okay? So this one is our convention. If the beam bends like this, then that is top fiber is in tension, bottom fiber is in compression, then it is, this will give me a diagram like this. So this is positive. Is it clear? So you must know what is a positive axial force that produces tension in the member. How did it come? So that is what we have taken here. So you should know, yes, it produces tension, increases the length. So it tries to increase the length of the member, so it is a positive axial force. Positive shear force is like this. The action is like this. Positive bending moment, it is this. So be clear about why it should be positive. So okay, we have drawn the bending moment diagram, and so this is normally the second problem that is covered in most of the books. Now third problem that supposing you have a cantilever beam, can you please maintain silence? So third problem, it is a cantilever beam of length L. Now this is this figure is mirror image of some people like drawing cantilever like this. Of course, length is not equal, because there is no space on my paper. So, but then this is what, this is a mirror image. So, either, so if this is subjected to, did we do with concentrated load? I have told you to do it. Let us not do concentrated load. We will do it. UDL also will not do it. UDL is simple. I want to load this with a load which is which is not uniformly distributed load. It is a varying load. So, from this side if you look, mirror length L. So, whether you solve this problem or this problem, you are solving the same problem. Advantage, it all depends upon how you look at it, because where you fix your coordinate, origin of the coordinate. If I solve this problem, if I take it like this, then there is some advantage in taking origin over here. Calculations are less, simpler calculation. There will be simpler calculations, otherwise. And if I take my origin over here in this problem, then the calculation slight complication, and complication comes because of trapezium. Because if I take a section over here x from left to this, then I have to consider a load that is trapezium in nature. But if I take a x from here, of course, x is now different. X is starting 0 is here, this end. This x is 0 is here, it is starting over here. L is going this way. So, my coordinates are different. Is it clear? In the here I am measuring my x from here to here. In that case, if I draw the free body diagram of this, then I need to consider only a triangular load. Is it clear? So, this will will be slightly simpler. So, let us say I want to find out now, first of all, yes, what is the free body diagram? Quickly, free body diagram. So, I will take this. At any support, the support is, this is loaded, it is not stable unless you put the support. What is the effect? What is the support? Support cannot move in x direction. So, there must be a reaction corresponding to that. It cannot move in vertical direction. So, there must be a reaction corresponding to that. We are drawing it in the positive direction, everything positive, positive x, positive z. Is it okay? This is my positive x, this is positive, and this is y is going into the plane. Plus, this support does not allow this end to rotate. Since it does not allow, that means there is some restraint, rotation. So, what is the force that will restrain rotation? It is the moment. That means you are, this bending moment. Bending moment about which axis? Y axis. It is y. So, although we are not writing y specifically, but it is about y axis. Bending moment about y axis. Now, I do not want to worry about what will be the nature of bending moment. I want to show here, because I am drawing, I have removed the, I have introduced a cut and I am drawing the free body diagram. So, I will take positive bending moment. On this phase positive, what is the positive bending moment? So, this is, so if this is my A, this is B, so this is BZ, this is BX, and this one what should I say? M, moment. I cannot say BY, then the meaning is not conveyed. Force by a simple, moment is restraining, it is restraining rotation. So, I will call it moment at point B. Is it okay? Positive moment at point B. So, like this MB, because if I use the letter BY, there are some books which will be using BYY, double subscript they will use. Double subscript means moment about axis. Single subscript means only a force. Double means it is a moment about YY, but still it is not clear. I think best thing is to use, yes, there is a vertical force, there is a horizontal force, and there is a moment, and moment about y axis. So, this is MB. So, this is free body diagram. So, first part is finding out, in any problem, is draw the free body diagram of the entire problem, entire body, and then consider equilibrium. How many unknowns are there? 3. So, it is statically determinate. We are solving only statically determinate problem. We are considering only statically determinate problem. So, therefore, this is all right. Now, can we write down quickly the conditions of equilibrium, which is the sheet 7. Conditions of equilibrium. Yes, please. So, we are considering this. So, horizontal equilibrium, sigma of H0 first. What do you get? Bx is 0. So, that means at the support there is no force in x direction. Clear? Vertical equilibrium. Yes, please. Vertical, what are the forces? Yes, this is a triangular load. What is the equivalent load? Triangle P naught L. This ordinate is P naught here. It varies from 0 to P naught per unit length. Is it clear? It varies from, intensity of load here is P naught. This is P naught. Intensity of load here is P naught, varies from 0. So, what is the total equivalent load? Total equivalent load is how much? You must have done this. P naught L by area of the triangle. Okay, and where is the centroid? Yes, so it will be here. So, total load is P naught L by 2, and this distance is 2 by 3 L. 1/3, 2/3. This will be 1/3 L, and this will be from this support 1/3. This will be from this end 2/3 L. So, this is okay. So, vertical equilibrium is, yes, vertical equilibrium is minus P naught L by 2 downwards, P naught L by 2, it is downwards. Is there any other force? Yes, this one is there, plus Bz. Is there any other force? No. So, then this one is giving me Bz is equal to P naught L by 2. So, vertical reaction has come out to be positive, and that value is P naught. Total load will be registered. What about bending moment, please? Please let us. Moment about which point? That is important. Where should you moment about A we should take? Why we should take B? So that the moment of Bx and Bz are 0. I do not want to bring in that, so that I am left only with my moment, which is unknown. So, that is, so I take moment of all forces about B. Okay. Now, do not get this B with this B, you always have this problem about B. So, then this is, if you take moment about this, what do you get? You get M, let us write simply M, not MB, does not matter, M, positive M. M is equal to or minus M is equal to P naught L by 2, P naught L by 2 into this distance into L by 3. So, that gives me M equal to P naught L square by 6. So, I have got so, this is the free body diagram. This is childish. So, this is, and the reactions are and moment is positive. So, this is M is P naught L square by 6, and this one is P naught L by 2. This vertical force is this, and so this is the free body diagram. And all the reactions are computed. So, this is known, this is in a state of equilibrium. This is, by the way, we are in this all such problems, we are invoking only the first condition of, and that is study of forces and equilibrium of forces. We are not going to deformation and force displacement relation. Okay. So, here we have done this, but was it necessary in order to find out bending moment shear force at any cross section to find out this reaction? What is happening? This only you are discussing this. Was it necessary? Because now I am interested in finding out at any cross section what is the state of bending moment, what is the value of bending moment, what is shear force, what is axial force. So, tell me, I could have done, because from here everything was known, left hand side. I could have worked from left hand side to the right hand side. But if you had taken this diagram, then from left hand side these support reactions were necessary. But right hand side your origin, then it is not nice to work backwards. You cannot take your x, then you will make mistake. X will be then negative. Yes, you can take your free body diagram from this side, but then you are always considering this face is negative face, while we are considering positive face. So what I am saying, if you take this diagram, then there was no need for me to find out this reaction. In fact, this reaction would automatically would have come if I had considered this when I am here. From that expression itself, when x equal to L, I would have got this. Okay, just a minute, it's okay. So this is, you please find out the values, plot the diagrams, bending moment and shear force, and study for yourself whether it should be positive, negative, and whether whatever you are getting the signs are right or not.